Thank you very much. First of all, I would like to thank organizers, first of all, Gennady Mishulus, who invited me and providing me the opportunity to make a presentation. All the organizing committee, Professor David Abrahams. So it's very nice to present, have the possibility to present my humble results. I'm here as a representative of applied science, so I'll talk. There will be nothing new about how to use factorization. It's just an application of Khrapkov methods to some problems. It's the problem to not expand the class of mathematical class of matrices that could be solved, but it's expand a little physical problems that could be managed to put inside of this class. Okay, so methylation, problem origin, it's from the literature picture, it's eliminations of coatings and separations of layers when layers of different properties separate due to mechanical tension, mainly due to thermal expansion. For questions of interest, usually dealing with problems of crack propagation, the most interesting point is to determine stress intensity factors, which is the singularity coefficient at singularity near the crack tip. It's a square root singularity for uniform material, or it could be a square root by oscillation term if it's dissimilar material. But in this problem, in this type of problem, there are other interesting point to find. When we have a delamination, when it's rather big compared to its thickness, or if it is bilinear, but the delaminated part are longer than thickness, so this part could be, it's interesting to model as an object with reduced dimension, like beam in 1D plate, or if it's curved, slightly curved plate, or shell. And it simplifies the problems a lot. And the point is to find proper boundary conditions, because first problems that it was solved starting with Abrimov work and then Kachanov work is to consider this as a rigid, pure rigid quantity, but it's not good. It's asymptotically correct maybe, but not enough. If we consider if it's a beam or a plate, like shift of this point and angle of rotation, these two shifts and angle of rotation as a combination of force parameters, we will have matrix of coefficients of elastic line. This matrix, just 2 by 2, was introduced in the beginning of century by Hutchinson, by Cottrell and Chen, as I remember, and then it was extended as this, so it could be and how to find it. Actually, if we solve this problem by considering it's uniformly extended to infinity in both sides, we can consider it as a problem for semi-infinite plate. Two plates, or plates on half plane, or two plates, and far apart it would be, the deflection would be polynomial, and coefficients of polynomials would be coincide with this one. So and if we solve it by applying Fourier Laplace transform, it would correspond. So this is in real space correspond to 0, this to infinity, and then transform space it would be vice versa. But it's still, we need to find asymptotics at 0 and infinity, and here we need only leading term, and to find this we need actually 4 terms of expansion up to 4th terms. Okay, so this is basic literature. It's the paper it's only basic. It's the paper I took as a basis for my research. It's group of work of Khrapkov, Zlatin and Khrapkov works. It's not this famous work, it's later works, most in Russian, only one in English, when he solved similar problem with this technique. And here are 2 my works on this subject. So, mathematical formulation. We have theory of elasticity, classical application, these 2 different properties, and we have equation of equilibrium, compatibility, equation of elasticity, and 4 elastic constant. Just 2 Young modulus, 2 Poisson's ratio, maybe actually Young modulus, Poisson's ratio, and shear modulus, only 2 of them are independent. And so for elastic constant, we can normalize for one of them. It would be 3 constant, but actually it was chosen by Dunders that only 2-dimensional combination, these combinations, which from -1 to 1, in most general cases even less, these 2 coefficients describe all the behavior. So the problem depends on 2 coefficients. So, and this is boundary condition, externally applied load. So we have the 2 problems solved. One is for 2 layers of similar thickness with different properties, and the other with layer on half plane. So we introduce 2-side Laplace transform. I followed by the work of Khrapkov, use it, but it actually, doesn't matter. So I use 2-side Laplace transform, and the part which is analytical in right half space is relative displacement, actually derivative of relative displacement, and here is stresses of the continuation of crack line. And it came to matrix in transform form. I did not wrote integral equation, it just appears from Riemann problem. This matrix coefficients for one problem and for the second problem. It's exactly of Khrapkov type, so it allows matrix factorization. And the point is, what's the difficult point, that this coefficient is at 0, it behaves like this. So sorry for this notation. I use notation that came from elasticity, so it could be difficult for it. For example, sigma, alpha, and beta are parameters, and p is parameter in the Laplace variable in Laplace space. So maybe it's a bit difficult. So the structure of this matrix at 0 is like this. Coefficient. So, partial indexes and at infinity the behavior is good. So due to this behavior at zero, partial indexes of this problem are in conventional notation 3 and 1. So it's also interesting behavior of the function at infinity and at zero. It's allowable behavior for the first problem, for half plane, and for street. So it allows different different behavior for these functions. This it's for normal and shear displacement and function. So what's that? Actually, following by work of Zlatin and Khrapkov, I have not found canonical solution. I obtained a solution and then choose the polynomial to satisfy these conditions at zero, at infinity. It's not obvious conditions, and that's why it would be anyway additional problem to find proper. Okay, this four independent solution, how it was chosen, it's from mechanics point of view that we have here four constants, four independent constants that could depend, that the solution can be called four independent solution, and here is how it appeared in reality. So, do I have time, and do I need to remind Khrapkov method of factorization? If we have matrix of course half trace, we can represent it in terms of four numbers: determinant, exponent, and commutant, which have two independent values, and representing it in such a way. So instead of four coefficients, we have four coefficients and not the determinant, exponent, and two in commutant. If we have two matrices with the same commutant, they are commutative, which that's why it's called commutant. And the properties how to operate with this matrix, how we can, so any matrix can be represented in such a way, just a moment, in such a way, square of determinant, then unit matrix by hyperbolic cosine of exponent, and commutant by hyperbolic cosine of exponent. And if we have two matrices with the same commutant, we just, for multiply there, it should be multiplication sign. We should multiply determinants and add exponents. And for calculating inverse matrix, it's instead of plus, it's minus. So it's very simple relations, and it allows immediate factorization of such matrices. For example, if our commutant composed of constant, so it's obvious we need to factorize determinant and factorize and split exponent, and so on. That's all. But if our commutants are not constant but simple polynomial, it is also possible to have a solution by applying such a trick. It's introducing such a function, and it's, despite it involves the square root, it should disappear in final because it appeared in even orders. So this trick is still applicable for such matrices when it's when the commutant is polynomial of not high order. So for returning to the problems that was solved, here are components of matrices that was for these two problems. So this eigenvalues, the pole was removed by so we have these two problems to solve. The first problem, factorization, here it's not a problem. It's very simple. Just have a pole, double pole, that it's by applying tangent function, square of tangent function. And the second problem is a bit more difficult. It's here the first problem. It's almost elementary. And the second scalar problem is difficult because this function has logarithmic singularity at 0. So, following by the work of Zlatin and Khrapkov, it's removed by adding and removing these terms. So these terms are added and removed, and this for the remaining part, it's became obvious, and plus and minus it could be done by Cauchy integration. So this trick, it's again not mine, it was explained in the work of Zlatin and Khrapkov. Then, because it's already a detail, I may skip it because I need expansion at 0 up to fourth order. I add and remove some functions so that it could be more easy to remove logarithmic singularities that appear due to discontinuity in the first derivative. And then final solution. After I obtained factorization, there was an additional problem to find this function applying Lewis criterion, and it was just done by considering the behavior of function that was obtained after factorization, expansion at 0 and at infinity. And it's interesting that at infinity the leading term appeared singular. That's why its additional applicable terms appeared that could be that do not violate condition at infinity, and at 0 it's okay. So all four conditions, all four constants are found by comparing with required behavior at 0. So we obtained here everything. For the first problem, for half plane, this term disappears. So here's the result. All values of interest are obtained in terms of U integrals that are written here. I don't want to go into details, but just I obtained all values of interest intensity factors due to all basic cases of loading and coefficients of elastic clamping. Here, one illustrative example: stress intensity factor of the second mode, and due to first Domdorf's parameter, and that could be from -1 to 1. Here is existing finite element solution. here the behavior obtained with these regions, it's very difficult to obtain numerical solution. So, conclusion is obvious. These groups of problems are solved. I have not managed to expand anything, the classes of matrices to be factorized, but I managed to find class of mechanical problems that could fit into this class. That's the achievement, and obtain solution. So discussion. What I want to discuss? Not solve problems actually. Not so obvious here. First thing. Mechanicians like to solve. There were good works of Koiter, of Calandia, that considered simplified problem. They replaced layer with beam from the very beginning with one-dimensional object, and obtained, instead of such a matrix, which are very simple, much simpler. So, but if we look at this, it means it's just leaving only the leading term at 0 here, and this is behavior continuity. So maybe the result obtained with this approach are not bad. I try to just remake this 0 and leave the whole terms. Obtain solution which is, it's just a game. That's not serious, of course. And this solution appears better than this, but worse, of course, than this. So, the problem is to find maybe some approximation to this problem. So, the role of indices, as we discussed. Okay, and one thing I would like to, what I not very happy with, it's this. No. Is this. Adding these three functions for removing singularity, logarithmic singularity, for me it's working, but it's not elegant. It's difficult to not to lose myself in branches when solving it. So if someone can find something better, it would be very interesting. Then, not solved problem. Not solved problem. Actually, what was done? Here is the matrix. But I forget to tell that it's the problem could be solved if for vanishing second Dundur's parameter. Only so there are two parameters. One is could be arbitrary. The second, what the solution could be obtained only for this 0. It's interesting. A lot of people solve this work. By the way, it corresponds to the case where there is no oscillation. So there is mismatch, but if this is 0, so there is no oscillation. And this particular case was solved. If it's not 0, it's the matrix became too heavy. Only constant, but the matrix crashed. So, anisotropic case. Matrix became much more heavy. Number of parameters increases. Actually, anisotropic and non-symmetric. I wrote general case. So it still look very similar, but instead of polynomial in commutant will have some sine, cosine, which became exponents in imaginary x. So, non-symmetrically, again, matrix are similar, but not, again, it cannot be solved by this approach. I understand that it could be done by approximation, some proper approximation, but I was usually told that if you do approximation, well, what's the reason? You can solve it by finite element. So, that's all. Again, thank you very much.
Thank you very much. Other questions, please?
I see that your approach and your solution change the situation at the crack tip. But if the layer is long and the load is applied far from the crack tip, what about energy release? Is it changed by your solution or not?
Energy release rate is actually I calculated stress intensity factors for all modes, and stress and energy release rate are obtained from here by generalizations of Irwin's formula. For the known cases for loading with pure moment, it coincides with classical beam solution.
It remains the same.
It remains the same. It brings contribution when we have, it remains the same for pure bending, for this shear. It changed for such application of such loads where we have contribution of this.
So this angle you mentioned,
Yes,
doesn't
due to existence of
affect if it is
yes.
long.
Actually, this was found by uniform case for plate on half plane by Zlatin and Khrapkov.
So the energy release could be found by a simplified model, but
Yes.
the resistance, energy resistance.
It's energy release can be defined by elementary methods for this mode and this mode, but not for normal forces, loading with normal forces that contribute. So the parts that contribute to moment, it's okay, but there are additional part, which is one power less of thickness of two lengths, but it still exists that it could be essential. Have I answered?
Further questions? Yes.
Can I just make one observation at the end of your talk? You mentioned if you have to go over to approximate factorization, why bother use some numerical scheme? I don't agree. I mean, I think first of all, observation is Khrapkov factorization or Khrapkov-Danieli is very special, and we should take great advantage for any matrix which we can actually factorize, because we've seen this week we almost can't solve any. So we have a class, and then let's use that as a way of perturbing to find some classes for non-commutative factorization which we can solve approximately but still preserve the singularity structure. So at the end, when you break the symmetry, you won't be able to solve them by Khrapkov factorization, but you will be able to if they have preserved a nice structure, which yours shows. Then you can somehow construct an asymmetric factorization, non-commutative, by that process. So I think you have a lot of mileage in what you do.
Thank you very much. And if I manage to walk here, and if someone will help, or if even someone do it without me, it would be very huge, I would be glad, and the community of fracture mechanics would thank. Makes sense.
But we can do it next week.
It's only common. First of all, we definitely will do it next week, but I remember
there were a few questions. Give us the matrix coming from the nature and having non-zero partial indices. We have the matrix already here, and actually this is singular perturbation of the Khrapkov-Danieli, and this would really come immediately to some philosophy. Hopefully, if everyone survives to my talk, there would be some philosophy about this.
That was the advertisement for this afternoon.
Yes,
right?
yes, yes. So
Perfect.
please stay. Would be no long formulas. This I promise.
All right. We'll take your word for it. All right. I think, are there any further questions? I'm guessing everyone's eager for coffee. So, well, let's thank Konstantin. Thank all.